Okay, um, so we have these two equations now. A plus B is equal to C. I'm going to call that equation 1. And I times K1 times quantity A minus B is equal to I times K2C. So I'm going to cancel the I's, and we're going to call that equation 2. Okay. Now if we multiply equation 1 by K2, then we get K2 times A plus B is equal to K2 times C. Okay, but then we notice that K2C from equation 2 is equal to K1 times A minus B. Okay, so this is equal to K1 times A minus B. Alright, so and so now we have K2A plus B is equal to K1A minus B. Alright, and this leads to the relation that B is equal to K1 minus K2 divided by K1 plus K2 times A. So this gives you a relationship between A and B. And again, A is the A squared is the density, is the number of particles per unit length, and so it's not arbitrary, as we discussed before. Okay, and then if we write this in terms of the energies, then K1, if you remember, K1 is equal to square root of 2me over h bar. Okay, and so all of these, all of the k's are going to have 2m over h bar in common. Okay, and so we can factor that out and cancel it. So what we're going to get is that K1 is equal to square root of E. This ratio is equal to square root of E times square root of minus E plus U naught divided by basically same thing with a plus sign. Okay, times A. Okay, so now if we multiply equation 1 here by K1, we get K1 times A plus B is equal to K1 times C. And if we add that to equation 2, okay, which is K1A minus B, so we're adding the left-hand sides and we're adding the right-hand sides, plus K2C, then we see that we have a K1B and a minus K1B, so these cancel. And so if we then solve for C, what we find is that C is equal to 2K1 over K1 plus K2 times A. And again, if we write this in terms of the energies, then we get 2 times the square root of E times the square root of E plus square root of E minus U naught. And I just realized that this up here, these should be minus signs. Okay, minus signs there. Alright, so now we have relationships between C and A and B and A, so everything is in principle solved, because again A is given by this sort of intensity relationship, the beam relationship up there. Okay. Okay, so now if we define the reflection coefficient, that is the probability that a particle that arrives at the potential step will be reflected, as the ratio of the intensities of the reflected and incident beam, then if we plug in the relationships for the intensities, we get this.